All right, general chemistry students, this is your Unit 6 review guide. I'm going to go through some of these here, not all of them, and then I'm going to put a link into the description with the answers for all of them. Not the work, just the answers, so you can tell if you're doing the work correctly or not. But this will serve as some examples for all the different possible problems. So we have scientific notation first. We're converting one way or the other. If we have a large number like this, we're going to be moving the decimal to the left until it gets in between the first two numbers. So it's 7.1. We count how many times we move that decimal. There's 3, 4, 5, 6, 7, 8, 9. So it's times 10 to the ninth. And then if we wanted to do a very small number like this one, 2.7 times 10 to the other direction, 1, 2, 3, 4, 5, 6, 7, 8. Decimal is there, minus 8. If we wanted to go the opposite, so we wanted to take it out of scientific notation, if it's a negative, we're going to be moving the decimal to the left, so it's 0, 0, 0, 0, 6, 1. That's because the decimal is, we have a negative exponent, so we're moving the decimal from here, 1, 2, 3, 4, 5 places. The other direction, if it's a positive exponent, we have 9, 8, 8, 0, 0, 0, 0. Let's see, it was here, 1, 2, 3, 4, 5, 6, 7, and we end up with our value there. Now this one here really wouldn't be expressed in scientific notation, but if we wanted to, it would be 1.876 times 10 to the second. Just moving the decimal two places to the left, so times 10 to the second. But if we have a value like this, it doesn't really make sense to express it in scientific notation. 1 mole of anything is going to equal two different things, 6.022 times 10 to the 23rd, or a mass from the periodic table. And that's the average atomic mass. All right. We have talked about this statement very often, super frequently. How is a mole is like a dozen? Well, a mole is a counting unit, just like a dozen. 1 dozen is equal to 12, or 1 mole is equal to the 6.022 times 10 to the 23rd. It's the same idea. So anytime we're doing a conversion with the mole, if we just think about it as a dozen, but we just write this number instead, it's the same work. For example, here we have 7.5 grams of water. We want to get that to moles. We have grams of water down here, moles of water up here. 1 mole is 18 grams. That value comes from the periodic table. If we add up 2 hydrogens and an oxygen, we get 18. And that comes out to be then 0.42 moles of water. We do the same process for these guys down here. We're going to go back the other direction now. We have our moles. So we're going to start there and convert to grams. So we have 0.0045 moles. Now let's look at this again. We have 1 mole. Put this up here. That can equal two different things. It can equal a mass. That comes from the periodic table. Or it can equal 6.022 times 10 to the 23rd. This could be atoms, molecules, formula units. Either way we look at it, or whatever it's called here, it's a particle. So some kind of a thing that we're counting individual objects of. So these are the types of things we can count in chemistry. Then 1 mole can equal one of those two different things. So if we're given moles, we either have to go this direction and use our value, 6.022 times the 23rd, or we go this direction where we have to use the mass from the periodic table. So here's my moles of sodium chloride. 1 mole. Notice my labels. And 58.45 again comes from adding up sodium and chlorine on the periodic table. Sodium is 23, chlorine is 35.45, so we end up with 58.45, and that gets us a value of 0.26 grams of NaCl. And these would be treated the same way. All right, I'm going to put this back up here so we can see the work. Scoot it over here so I have room. We have 1 mole again. I'm going to color code these guys. There's a mole. We can go to then grams. That comes again from the periodic table. Or we could go, let's try this one. Yeah, that works. 6.022 times 10 to the 23rd. So I'm given grams, which means I'm going to start with my mass from the periodic table as my first conversion. So here is our 8.24 grams of silicon dioxide. Now I first have to get to moles. So here is my grams of silicon dioxide. Go to the periodic table, and that comes out to be 60.1. And then we're going to go to our 1 mole of silicon dioxide. Grams cancels. One mole of silicon dioxide. And now we have to go to other one, 6.022 times 10 23rd molecules. And it gets our number of molecules, going to be 8.26 times 10 to the 22nd. Remember that molecules is different than a mole. A mole is a counting unit. Molecules are individual pieces of a covalent molecule. So this is a particle. Atoms, molecules, and formula units are particles. All right, so we have another problem here. Oh, that's too bad. Where instead we're just starting with moles. So we have our there we go, 6.32 moles nitrogen oxide. 1 mole is going to equal 6.022 times 10 to the 23rd molecules. So this disappeared, so rewind just a little bit so you can see this. We're starting in the middle with moles. We're going to molecules, so it's just going to be one step. Start with moles, go to molecules. We end up with a value of 3.8 times 10 24th. Molecules. So there's our answer there. All right, now I'm going to rewrite this back up here now after it gets erased. And let's start with that 1 mole in the middle again. And then we're going to go back over here where we had our grams from the periodic table. And then we're going to go the other direction over here where we have that number of particles. So in this case, we're going to be starting with our formula units, which is, again, one of the particles. We have atoms, molecules, formula units. Starting with formula units, we're going to then go to a mass. So the first thing we have to do is convert to moles, and then we convert to a mass. We have formula units down here, and that is equal to 6.022 times 10 to the 23rd. 1 mole. There's my mole step going to moles, and now I can go to our 58.45 grams. Cancel things out. Formula units of sodium chloride cancels formula units of sodium chloride. NaCl cancel with this NaCl, the moles. We're left with our grams of sodium chloride. So we can see we started with our formula units, sodium chloride, then went to moles. From moles, that's here, we went to our grams. All right. Number 8, 1 mole of oxygen weighs 32 grams, while 1 mole of hydrogen weighs approximately 2 grams. How is this possible? Well, oxygen has a larger atomic mass. So if we think about this in terms that 1 mole is always equal to this many, it's the mass of it is going to be dependent on how large an individual atom is. And so an individual atom of oxygen weighs more than an individual atom of hydrogen. It's kind of like saying if we had a dozen, I don't know, feathers and a dozen bricks. It's very easy to see that the bricks are going to weigh more because each individual brick has a larger mass. So in this case, oxygen is the brick, hydrogen is the feather. All right. We have percent composition by mass. Our iron 3 oxide. Remember the percent composition, any kind of percent value is going to be the part divided by the whole. And so the whole is going to be the entire molecular mass of this thing. So we have, let's do this again. The entire molecular mass of this iron 3 hydroxide is going to be 106.88 grams per mole. It's the molar mass. That comes from the periodic table. I added up the iron, 3 oxygens, 3 hydrogens. Now we have the part, which is going to be our iron, 55.85, divided by the whole. 106.88. I'm going to leave labels out here because they're not important to keep track of when we do these kind of problems. And so it's easier to see the math. So we divide those two things. We end up with 0.523. We have to convert that into percentage. Move the decimal 2 places to the right. We end up with 52.3. Now I can do the same thing with the oxygens. Oxygen is going to be 48. It's because each oxygen is 16 and there's 3 of them. We divide that by 106.88, and that gets us a value of Large number, almost 45. All right, and then we can do our last one. Our part is going to be hydrogen this time. It's going to be 3. We divide that by the whole. It gets us our answer of something very small, 2.8%. And we'd apply that same process to the rest of them. All right. Here's an empirical formula problem. We're going to do 2 different empirical formula problems because we have an empirical formula here with percentages, and this one here is going to give us an empirical formula with straight masses. So let's look at this one first. We have acetic acid, which we do not have the chemical formula for. That's what we're after. An empirical formula tells us the subscripts in the chemical formula. So we have different percentages of the 3 different elements in this. So this thing is going to have carbon in it, hydrogen, and oxygen. And we are looking for these subscripts. Remember that the empirical formula is the lowest whole number mole ratio of these elements in this chemical compound. So the key word right now that we need to focus on is the mole. We need to convert these values into moles so we can get a mole ratio. To do that, we convert those percentages into masses. Now, since we just got done doing work with masses, percent by mass, we know that when we see a percent value like this, we can treat it as a percent by mass. So if we have a sample that is 100 grams, we can say that 39.9% of this is carbon, or 39.9 grams of it is carbon. We can apply this same concept to any kind of sized sample. This just makes the math easy. All right, so there's my grams of carbon. Convert that into moles. We can do the next one, which is the hydrogen, 6.7 grams of hydrogen. 1 mole of hydrogen is 1 gram. I'm rounding these values just a little bit, guys. So if you use like 12.01 and 1.008 here, you'll come up with just slightly different numbers than I do, but the overall answer will still be the same. All right, now we have oxygen, which is 53.4 grams of oxygen. We have 16 grams of oxygen is 1 mole oxygen. Do the math for each of those. We end up with 3.32 moles of carbon, 6.64 moles of hydrogen, and 3.33 moles of oxygen. All right, so this is our mole ratio. We have this mole ratio, but these are not whole numbers. So we need to get these things into whole numbers. To do that, we're going to divide by the smallest. So we'll divide by this one. If we do that, we get a whole number 1. Now we have to maintain the ratio. To maintain the ratio, all of them have to be divided by that. This is almost 1. Oops, I did that wrong. That should be 3.32. That's almost 1, like it's just barely off. Sometimes, yeah, and we round these guys. Remember, if it's very close to a whole number, 2.99, 1.001, something like that, we round to the nearest whole number. This comes out to be 2. So our answer is going to be C, H2O. There's our empirical formula. All right. Now we're going to do one with masses. It's the same process, only in this case, I'm going to color code this time. We have a compound with phosphorus and chlorine. All right, so here's my phosphorus, and we'll do, here's my chlorine. So if we have masses, we don't have to worry about changing them into masses. We don't have to do like a percentage thing and figure out what percentage of 100 grams is that sample, all that extra work. All we have to do is to use the mass that's given. Since we have 11.39 grams of phosphorus, we can just use 11.39 grams of phosphorus and convert that into moles. Here's my grams of phosphorus. 1 mole of phosphorus. And let's see, grams of phosphorus is going to be 30 point, or I'm going to run 31. End up with a value of 0.368. There is that. Now if we look at chlorine, we don't have a mass of chlorine, but we have a total mass of the sample. So if we subtract those two things, our chlorine is going to be 50.51 minus the phosphorus, which is 11.39. That will get us our answer for chlorine, and that is 39.12. So now I have my mass of chlorine. I can convert that into moles. Uh, 1.10. That's very close to, if you want to get one more decimal, I think it's 1.104. So we can divide by the smallest, which is going to be our phosphorus, 0.368. That gets us the whole number 1. We divide it by the same thing down here, 368. Gets us the whole number very close to 3. So our final answer for the phosphorus chloride is going to be phosphorus trichloride. All right, so that's where I'm going to stop here. I'm going to, again, make a document with all of the answers like this in it, and I'll link that in the description. And you can use this to review for the test.